Hello, my name is Andrew Rush, and this is my Physics 2211 Lab 2 about projectile motion. For the introduction, so the purpose of this lab was to analyze the projectile motion of an object and compare that to a computed simulation in regards to just gravity and then with gravity and air resistance. Some models and principles used in this lab was our system was a scrunched paper ball. Our surroundings was the Earth's air. The models that we use were the Tracker app, GlowScript, and Excel. And in addition to that, we had some formulas was the net force formula, position update formula, velocity update formula, and drag force. Something to note that the net force is equal to the force of gravity with the absence of a drag. Some initial conditions was that an object lays at hand at this position. When we calculated delta Rx over time and delta Ry over time, the change in position in both the x and y direction, with an initial velocity of negative 1.321 and 331 meters per second. So without air resistance, B, the drag force constant has a constant of 0, and without air resistance, it has a negative 0.0081. In this case, B is negative because the object was thrown from right to left, so the x direction is negative, and B is opposite to the direction of motion. Our observed was the tracker object data selection. So a brief result, this lab revealed a relationship and accuracy of projectile motion and Newton's second law of motion and showed how air resistance is almost negligible, but in reality the motion of this projectile falls faster than computed. Some observed experiment details. We threw a crumpled ball across the screen. It had a max height of about 0.6 meters, traveled a distance about 0.76. The mass was 0.004 kilograms, and its time was about 0.67 seconds. And the tracker was done manually since the automated tracker did not function, and the video was held still. As you can see, there's just some data and pictures of the ball getting thrown across the screen. And this was the tracker app at the top right. It's the tracker app tracking the object's motion. In addition to this, the drag constant, like I said, was a negative 0.0081. And then with gravity only, the models on the right, position and velocity update formula in a while loop for entire trajectory. Initial conditions determined from observed calculations, and as I said before, the net force is equal to the force of gravity. However, with gravity and air resistance, the force of the drag force is equal to the negative of the drag constant times velocity squared over v hat, and now the net force is force of gravity plus the drag force. It's a minimal difference, but it cannot be neglected entirely. Some assumptions: we assume that the position from the center of the ball and only considered forces are drag and gravity. Some discussion. Similarities and differences. The observed trajectory graph shows the most diverged skew toward the end, while the gravity and air resistance computational model holds the most similarities with graph's overall trajectory. The computational model with only gravity is the most diverged, which is reasonable since it assumes unrealistic circumstances. Both graphs have the same starting positions and fairly similar initial velocities. Also, all peak at relatively similar points and times. The computed gravity and the drag force proves the accuracy of Newton's second law and the effects of gravity and drag on a system. Some potential sources of error were the manual time steps on the tracker, assuming the center position of the ball, its initial force of motion, and inaccurate tracker scalars, and the trial and error of the B constant. So what if we were to repeat the experiment but throw the ball straight up? In this case, there would be no x component of velocity. However, this does not neglect air resistance or gravity. Calculating this would take in for a vertical motion, which would be the time up plus the time down, which would be 2 times the initial velocity over gravity. Since there is only a y component of force, therefore it would take the same time, if not longer, to reach its final position versus a trajectory motion. And what does this mean? Terminal velocity is not expressed in the computational graphs because the object is not in free fall and therefore does not experience a zero net force. A similar experiment conducted would be dropping small parachutes with different weights at the same height to see the effects of gravity and air resistance changing to reach a terminal velocity. As you can see, these pictures here, you can see the average terminal velocity versus my terminal velocity. So overall, this lab was very successful in proving Newton's second law and projectile motion, and it was very successful. Thank you so much.